Okay, hello again, and welcome back to the last chapter in the book. You've made it very far. I'm very proud of all of you. And the title of this chapter is The Lie Series and an Introduction to PDEs. So, in fact, the person that the Lie series is named after is Sophus. It's an S. Sophus Lie. I think he was Swedish. You can look that up, though. And he had some really nice ideas on, more or less, you'll hear stuff about mathematicians speak about Lie algebras and Lie groups. And in fact, Lie groups are manifolds, and you think of manifolds as things which behave like Euclidean spaces when you zoom in close enough. So these are surfaces which are flat locally, so something like the surface of the Earth is locally flat. But it's a manifold, which is also an algebraic group. So if you've taken an abstract algebra course and you know a little bit about algebraic groups, groups are objects and manifolds are objects, and there's an overlap between the two, and the intersection of those two mathematical objects are the Lie groups, and then the Lie algebras are the tangent spaces to the Lie groups. If you know what a tangent space to a manifold is, you could think about that as like the locally flat derivatives that you can encounter upon some surface. Like a tangent plane to the surface of the Earth is a tangent space. And the reason why the first one is a group is just by definition, but the reason why the second one is the algebra is that these algebras are actually equipped with both their vector spaces. All manifolds are going to be locally vector spaces, and then their tangent spaces are vector spaces. They're algebras because there's actually a well-defined multiplication on that vector space as well, and it's the Lie bracket is the multiplication on that vector space. But anyway, why do we have the series here? What does the series have to do with all of that? Well, it has to do something somewhat, for now it won't seem like it's related, but if you go into kind of a subset of ODEs and PDEs known as control theory, this actually has a huge amount to do with Lie algebras and Lie groups. And so if you get interested in the idea of control theory, which basically says, if I have the ability to modulate the forcing on a given differential equation, where can I reach in space, right? What trajectories can I follow if I'm able to be in charge of a forcing term? And it turns out Lie algebras and Lie groups are very important to control theory. And that's really the connection there. And then the introduction to PDEs, I don't think any of us will need explaining as to why there's a relationship between PDEs and ODEs. So that's where we're headed today. And today we're actually covering two sections, 14.1 and 14.2. 14.1 is the Lie series itself. I'll introduce the Lie series, and then in 14.2 we'll see maybe some relevant applications of that. So in 14.1, we have ourselves a theorem right away, which is a really, really elegant theorem. It says the linear solution to a nonlinear IVP. And that just seems like something that shouldn't be possible, but it is. And the way this is going to work is that we're going to start with a nonlinear IVP, but we're going to reinterpret it. So let's reinterpret the IVP in this setting, where now phi is a function of time, but it's also a function of our initial condition, is the flow map. And in fact, now I'm reinterpreting this as a PDE, right? This is a PDE. You can see I have a partial t right away. And then I actually have this d phi right there. And I'm sure you all know where this is headed. D phi is the Jacobian. So the Jacobian of phi. And then I'm multiplying that by n coming from there, but the n is just on x actually. So I have this interesting partial differential non-autonomous Cauchy problem, but in fact it is linear. So there's a PDE here, but it's a linear PDE, and it is expressed as a Cauchy problem. Now let's make it a little bit more clear. How do we interpret this as, our traditional Cauchy problems that we have in chapter 6? If you actually clicked on this theorem, 6.5.5, looks like d dt of x equals L on x, and then x has some maybe initial value, x at t0 is equal to x0. This is the whole reason why we covered that chapter, functions as infinite dimensional vectors. You can imagine if I replace x as a vector with an infinite dimensional vector, aka a function, phi, let's replace x with phi. And it's a function, so phi actually depends on both t and some vector space x. But on the bottom right there, that's just an x actually. So this is phi naught of x, and then this is comma x, tx. Then I actually have a Cauchy problem in the variable phi, but it's an infinite dimensional vector. And in fact, L as part of this Cauchy problem, if I take phi equals L phi, and then phi at time 0 as a function of x looks like some phi 0 of x. This is an infinite dimensional Cauchy problem. And L here is d, and then it takes in its argument, phi, and then it multiplies that by n of t. So let's verify really quick that actually an L of phi, which is defined by d phi dot n t x, let's verify that that is linear. Because that's really what L is getting defined as. L is defined as the d and then the dot ntx. And maybe I should put a subscript t here. That's what makes this non-autonomous, because n depends on time. Let's verify that that's linear, and let's head over to the whiteboard and do that. So L t phi defined by d phi dot n t x. X is fixed. Let's see if this is linear. A phi plus b psi. I want to be able to distribute L and exchange it with those scalars. Let's just do it by definition, though. By L's definition, this is d of a phi plus b psi dot n t x. And the way the derivative works is this. The derivative, Jacobian derivative, is linear, which we're lucky about. This is a d phi plus b d psi dot n t on x. And thankfully, right multiplication, now this is unfortunate that we have to work with right multiplication because we're dealing with matrices, but right multiplication is distributive. And so we end up with equals a d phi dot n t on x plus b d phi dot n t on x. And this is exactly by definition of L, a L phi plus b L psi. That should have done psi right here. And so there you can see actually that this operator, the right-hand side operator, if I jump back to the book, the right-hand side operator is in fact linear. It doesn't necessarily look like a linear operator, but it is a linear operator, which means that this is a linear non-autonomous Cauchy problem. And in fact, I haven't finished the theorem yet. In fact, yt is equal to phi of t comma x. Okay, so if I solve this nonlinear Cauchy problem, or linear, if I solve this linear Cauchy problem, then I actually have a solution to the nonlinear IVP. And that's something that's really nice, really, really nice. That means all I need to do to solve some nonlinear problems is solve some linear problems in an infinite dimensional space instead. The proof is not too bad. So since we're restricting ourselves to analytic functions here, like I'm supposing that we are starting with an analytic n, then we just expand everything as a Taylor series, and you immediately see that all of the terms of the Taylor series agree. There's a second proof that doesn't require analyticity. It just requires that we're differentiable, I think once in both x and t, which is what you would expect out of something like the Card-Lindelöf. But then we get down to the next definition where we define the Lie series, okay? Because the Lie series is actually defined on a autonomous dynamics. So suppose that I'm not working with n sub t, I'm just working with n there. That's going to force this linear operator is no longer, the linear operator is no longer non-autonomous, it's now autonomous. This would be L. It's no longer L of t if I get rid of t. And so if I start with the autonomous dynamics, I have an equivalent autonomous Cauchy problem that I can solve. And we all know how to solve autonomous Cauchy problems. It's theorem 6.3.2. And the solution is given by exactly this series, right? We have to be careful about what does this power mean, right? Because there's the gap right there. It's D, and then there's an opening. So when I'm taking powers of this linear operator, I'm making sure to nest them right there. So we nest powers of this operator here. That's important, that you nest the powers of the operator right there. So you end up with something like d of d of d, and then, you know, with n being 3 or something. If n were 3, it's d of d of d of x, close it, dot n of x, close it, dot n of x, close it, dot n of x. So this is like the third power of the operator, L cubed. So you have 3 d's on the left and 3 n's on the right. And make sure that you put the brackets around each successive term, so you're taking the Jacobian of the entire piece, including n at each step. So, you know, it gets a little bit complicated. It's a bit of a complicated linear operator, but it's definitely something your computers can handle, right? It's just Jacobians and matrix multiplication. So So your computers could definitely handle this operator and could handle powers of that operator. And what you get is the solution to a nonlinear IVP. And so let's see this in action with the next example. We're going to compute the Lie series solution to this one-dimensional IVP, and I know everybody already knows the solution to this IVP. But if we take the Lie series approach, we say, okay, our equivalent Cauchy problem is partial t on phi equals, that's a square, right? So then you get partial x on phi, that's the Jacobian in one dimension, multiplied by n of x, which is just x squared. And then we have that phi at 0, or t0 on x equals x. And so to solve that Cauchy problem, we just go through this procedure. And there's our procedure. We're taking, iterated copies of x squared d over dx to the n. That x squared is because that's y squared there. And actually, if we calculate what every iterated copy of x squared is going to look like, on x it looks like this. And it's just t minus t naught x to the n, where this is actually the geometric series, meaning that circled in purple there, that's 1 over 1 minus t naught x. And if I have an x out front, that multiplies on top, and I actually recover the original flow solution that I was going to expect. So that's how the Lie series works, at least in one dimension. And then in higher dimensions, we can find maybe a Lie series solution to the following. So the Lie series solution to this IVP, all we have to do is properly define n, right? N's the right-hand side here, and then remember how to nest our Jacobian, okay? So we're going to properly define n. N maps the vector x, which is x1, x2, it maps it to x1, x2 minus x1, and then x2, x1 minus x2. And then we properly nest our Jacobian, and we calculate this on a computer, right? So use some sort of nesting. Or iteration on your computer, and what you get is the Lie series solution here. So if I calculate this out to 3 terms, this is my Lie series solution, and all I'm doing is computing the Jacobian on each successive term. And what I can write then is an approximation of the Lie series. If I truncate at 3, my Lie series has an approximation in red, which is just everything that's listed here, to the true solution in black there. And you can see it starts to diverge eventually. And then I also have my approximation in orange to the true solution in gray. So, your computer actually iterates on the Lie series very, very quickly compared to some other methods. Of course, Runge-Kutta often is used instead, but the Lie series has some other nice applications. So your computer iterates on the Lie series pretty quickly, and you get a fairly nice approximation in no time at all with the Lie series. So that's the Lie series in generality. And then we'll see some application examples in the next section. So this section is called separable ODEs, the Lie series perspective. Turns out we can solve separable ODEs with the Lie series, and the method of characteristics. So the method of characteristics is going to be one of our introductions to PDEs, and then in section 14.3 we have another introduction to PDEs using some of the techniques that we've developed. But the first thing I'll cover is separable ODEs from a Lie series perspective. Okay, so the first thing I'm going to talk about is what it would actually mean to try to go for a closed form solution. Right? When L was a matrix, we had a very nice closed form expression for this matrix exponential. But now if we're jumping into our infinite dimensional Cauchy problems, then we no longer have like a matrix exponential. We would need some sort of operator exponential, which we'd have to get by somehow diagonalizing an operator, or maybe finding a Jordan form for an operator. And these are not easy things to do. You'll need a functional analysis course, and in a lot of cases, a second semester of a functional analysis course to kind of tackle these topics of what it would mean to get some sort of diagonalization of an operator. These come down to the word spectral theory of, in one case, like normal C-star algebras. The one that I often use is the one for compact self-adjoint operators, but it's a relatively tricky theory to get into to try to define even closed form expressions for those matrix exponent or those operator exponentials. So it's not something you really want to get into right now, but we can do it in a couple specific cases. So the next proposition gives me one of those specific cases. So this proposition says that the exponential of the derivative is a shift. Okay, and what we get here is we're saying e to the t minus t naught, and I take a partial derivative in x against some function phi of x. That's actually a shift by whatever coefficient we have up front, t minus t naught in this case. Okay, and the way that you prove this is not too bad, actually. It's because you can solve this Cauchy problem exactly, and you find out that the solution is precisely the shifted function. And so you know that is the exponential, the operator exponential. So we can use that to go to the next proposition, which is the solution to separable ODEs another way. And so if I start with my nonlinear IVP here, which I know I can solve with the separable method, right? I have a phi of t over psi of y. If I jump back to my separable methods back in section 11, I believe, then I get, or chapter 11, then I have a solution of this. But in fact, I also know I have a solution of this using these operator exponentials, and that's really something cool to talk about. So the way this works, this is the same solution it looks like in chapter 11, where I define the antiderivative of lowercase phi and the antiderivative of lowercase psi as capital phi here and capital psi there. And if I have an inverse for capital psi, then I can push everything to the right-hand side. So this should feel very familiar for kind of your classic separable, nonlinear separable ODEs. But we can also prove this using our Lie series. So let's jump over here to the Cauchy problem for the flow map. And the Cauchy problem for this flow map looks like this. That's our linear operator in the Cauchy problem for the flow map. So I want to somehow get an expression for the exponential of this operator. If I just go to my right section in chapter 6, I know that the solution is this operator exponential. It's e to the antiderivative of phi and then 1 over psi partial x. So here you can probably start to see where I'm going to use that previous theorem where the partial x gave me a shift, but it gave me a shift by this much. I can't say that's true when this depends on x anymore. I have to be a little bit more clever. So when my denominator there depends on x, what I can do is rewrite this power in the operator exponential as this power in the operator exponential, where I've used capital psi and capital phi as the antiderivatives of psi and phi respectively, right? Because my chain rule is going to give me lowercase psi dx right there, and my fundamental theorem of calculus gives me capital phi's right there. So that's actually what's happening in this situation. And now I'm going to give myself a change of variables where this denominator I'm going to call z. And then I'm also going to shift time by phi inverse. So now time has been changed in variables by phi inverse. And so this just looks like tau minus tau 0, right? That temporal shift transferred me to tau minus tau 0. And my differential direction became psi of x. It was always psi of x, but it becomes z when I'm making the change of variables, and then that modifies x into psi inverse, capital psi inverse. Now I can apply the previous proposition right here because this is a true shift by a positive tau minus tau 0 by that proposition, and that sends me here. And then under an inverse change of variables, I'm going to take tau goes to capital phi t, and I'm going to take z goes to capital psi x. I recover my solution in true time dependent on a true x. And this is exactly the solution that the separability method gives us. But it's kind of really cool that we can see ourselves get it by calculating these flow maps instead and operator exponentials. So that's really cool. And then we're going to move on to actually the method of characteristics, which I get for free. And it's something that is usually taught relatively early on in an ODEs course, usually from a simpler perspective than you're going to see it here. So that kind of also emphasizes the power that we have with this flow map and kind of solving the nonlinear problem with the flow. But this is actually headed in the reverse direction. So the way the method of characteristics is working here is I'm actually going to start. Let's suppose I start with a linear Cauchy problem in infinite dimensions. That's of a very specific form. This is a linear Cauchy problem in infinite dimensions, aka a PDE. This is a first order linear PDE. First order because there's one derivative and there's another derivative. I have a derivative in space with capital D and derivatives in time, partial t. And so this is actually this is a general first order linear PDE. And what I know is that I know I can solve this. I know I can solve this as it's a Cauchy problem. I can solve it use techniques from chapter 6 to solve this, since it's a Cauchy problem, since it's a linear Cauchy problem. But I get something else for free. I get that, in fact, the solution methods that the linear Cauchy problem give me are actually flows. The linear Cauchy problem tells me that I have flows which solve this problem. This would be Duhamel's formula, right, or Duhamel's principle. So go back to chapter 6 and look up Duhamel's principle, and you'll see how to find the solution to this with some operator exponentials. But what I know from the Lie series is that those operator exponentials are actually flow maps. They actually flow me forwards in time. And so we get that the solution, this looks like the Duhamel's solution. It would be Duhamel's if I put my exponentials out front here and kept this as an x, and put my exponential there with Duhamel's. But I can reinterpret the exponentials as flow maps because of the Lie series idea. And so these flows, phi sub t0 and phi sub s, are actually the solutions to the dynamics given here. So all I need to do is solve. Hence, first order linear PDEs may be solved instead by solving flow maps for dynamics. And these dynamics are ODEs, flow maps for ODE dynamics. Now, they're often going to be nonlinear, in which case your life hasn't necessarily gotten any easy. But in the subset of situations where these are actually linear flow maps, then you can solve those exactly, which lets you solve those exactly. So that's something that's really, really, really cool. So the proof here is just what I was saying. You basically take the converse of theorem 14.1.1. And that's telling me that the operator here, which is the operator exponential of this Jacobian, and actually this one here is kind of the Magnus expansion operator exponential of the Jacobian, because my dynamics might depend on time. They might be non-autonomous. But whatever that happens to be, I know it's actually composition with the flow map. And by knowing that this is a composition with the flow map, then I know that all I need to do is solve the dynamics, which gives me the flow map, and then I reinterpret the Duhamel's principal answer in terms of the flow maps. So let's actually look at an example of that. Here's a good example in one spatial and one temporal dimension. So this is a first order linear PDE in one temporal and one spatial dimension. We're going to solve it. The first thing we're going to do is we're going to jump up to the previous theorem and figure out what we need to identify, right? So from this theorem, I need to identify, if I've decided I'm a first order IVP, linear IVP, I need to know what n is, I need to know what f is, and I need to know what g is. So let's scroll down here to my example. It looks like n is tx squared. N sub t of x is tx squared. It looks like f is t squared x. F of t comma x is t squared x. And it looks like g is cosine x. So as it relates to my previous theorem, the method of characteristics, I've now established n, f, and g. And I know my solution will be given by this so long as, right, so it's clear this is g, and this is f of s comma phi. And that's g of phi. Okay, so my solution will immediately be given by this expression just because of how I know f goes there, and then you put a flow map in for x, and g goes there, and you put a flow map in for g. But what I need to solve then, what I still need to know is I still need to know the flow map. I still need to find the flow map. Okay, so let's go ahead and find that flow map. The flow map corresponding to the dynamics with n. And so I replace the right-hand side of my dynamics, y prime equals n. I replace that with whatever n is, n of t comma y. So the right-hand side of my dynamics is ty squared. And thankfully, this is separable. And so we solve this separable ODE using separability methods, and we recover that the flow map is precisely this. This is a flow map initialized at s, right? So we have to keep that in mind when we use the method of characteristics, that we need the flow map initialized at any point in time, at any point in space. And this is the flow map we recover, which allows us to place that in up here and up here for these flow maps. This one's been initialized at 0, that one's been initialized at s. Okay, so we place this flow map into those 2 points in our solution map, and then we can solve the integral if we want to. We go ahead, cosine's kind of stuck the way it is, and if we solve the integral, we see that we actually have this interesting expression with a square root and an arctan. But that's really, really interesting, because you would have never thought that all it would take you to solve this PDE, which is not a trivial PDE by any means. It's not a very easy PDE to solve right away. All you need to solve it is solving this flow right here. Okay, that's all I have, and that actually finishes our semester, but I will have a video on section 14.3 that you should see on the channel soon. Anyway, I'll see you in class. Bye.